Indiana University East, School of Natural Sciences and Mathematics. Solutions to the electron in an atom problem. So an orbital is a one electron wave function. And if you think about the hydrogen atom problem, that's how we can look at it. We have one nucleus, the nucleus, so we have a +1 charge here, of electron here, and they're separated by this distance. And we can solve the Schrödinger equation for this potential function. Now, clearly I can't ask you to solve this, and there's a lot of intricacies in this that I'm not going to go through at all. But suffice it to say that there's an infinite number of different solutions. So these are wave functions that are possible, and each solution is classified by a set of quantum numbers. Okay, so each solution is identified by a set of quantum numbers, and here are the 4 quantum numbers that exist. Firstly, we have n, the principal quantum number. Then you have L, the angular momentum quantum number. ML is the magnetic quantum number. And MS is the electron spin quantum number. So, each electron in an atom has a unique set of quantum numbers. It's like your address at home. Each home has a unique address, or so we hope. Okay, and this idea that each electron in an atom has a unique set of quantum numbers, and hence having a unique wave function, is given by what's known as Pauli's exclusion principle, which we'll get into later on. Let's look at each of these quantum numbers with a bit of detail. So, principal quantum number n we've seen before. And n, as you may recall, the energy of an electron in a hydrogen atom depends on n only. And the n value really defines which electron shell you're in. N can take values of 1, 2, 3, 4, 5. A positive integer, in other words. Okay, so this is coming straight out of the Rydberg equation. The n in the Rydberg equation is the principal quantum number. Okay, and really n is related to the size of the orbital. The larger n is, the larger the orbital is, and the higher the energy. Then L, okay, obviously we're projecting this, is the angular momentum quantum number, which gives you the shape of the orbital. And L is equal to 0, can take values of 0 through to n minus 1, and each L value has a letter associated. So for example, if n is equal to 2, then L can be equal 0 or 1, because you can go from 0 to n minus 1. 2 minus 1 is 1. Now if L is equal to 0, we have S, and if L is equal to 1, we have P. So you can have a 2s orbital or 2p orbital. And electrons are the same, n and L are in the same subshell. Okay? You should note that if you have a multi-electron atom, the energy depends on both n and L. And this is something that hopefully we'll talk about later. Thirdly, you have the magnetic quantum number, which gives the orientation, again, of the atomic orbital. It takes values from minus L to plus L. So for example, if we look at the 3D subshell, okay, so D, as we said before, and you do need to memorize S, P, D, and F, okay, turning this back, you do have to memorize this. So we see that D means that L is equal to 2. So the possible ML values are from minus L, so that's minus 2, through to plus L, so that's plus 2. So it can be minus 2, minus 1, 0, plus 1, and plus 2. And for a particular atomic orbital, you will find that there's a value of N, L, and ML. Finally, you have the spin quantum number, which books would say different things about what spin means. Essentially, it is an intrinsic property of an atom that doesn't really have a classical analog to it. But what it does do is that if you put an atom beam in a magnetic field, you see the electron splitting into two different beams. Okay, and you can have a spin up, and the values for electrons for the spin quantum number is either plus half or minus half. So you have spin up or spin down. And quite often we represent these on orbital diagrams with arrows. So each orbital, in each orbital we defined N, L, and ML, right? We left MS free, so MS can be plus half or minus a half, so that's two possibilities. So that means that you have two electrons per orbital. One will spin up, one will spin down, and that's what we call a pair of electrons.